For a small herbivore, the forest canopy is crowded with predators that hunt by sight, constantly scanning the leaves for the slightest hint of a meal. Every step in the open carries a risk, until you run out of luck. But an entire order of insects, the Phasmatodea, better known as leaf and stick bugs, has opted out of this physical arms race. They don't build heavy armor or develop venom. They survive by becoming part of the background. Take a look at this macro view of a leaf insect's back. Over millions of years, they have evolved anatomical details that match the texture of their environment. Physical raised veins and patches of fake brown rot. Because a static leaf in a breeze would be suspicious, they pair this physical costume with a specific movement. By rocking back and forth, they replicate the rhythm of plant matter blowing in the wind. There is a limitation to this strategy. Staying perfectly still works well for avoiding a passing bird, but an animal eventually has to move. You have to break cover to forage for food or find a mate. Surviving while moving in the open requires a completely different approach. If you can't stay invisible, you have to convince predators that you are too dangerous to eat. In the insect world, ants are heavily avoided. They travel in massive, aggressive swarms, possess thick, chitinous armor, and often taste terrible due to the formic acid they produce. Predators generally give them a wide berth. This creates an evolutionary loophole known as Batesian mimicry. If a harmless, tasty animal can successfully impersonate a highly dangerous one, it gets to borrow that reputation. This diagram compares the silhouette of a standard jumping spider to an ant. Jumping spiders are highly vulnerable to spider hunting wasps, so over 300 species have evolved to mimic ants. But there is an obvious anatomical problem to solve. Spiders have 8 legs and 2 body segments. Ants have 6 legs and 3 segments. The spider physically alters its profile to match the ant's anatomy. It develops a constriction in its abdomen, a fake waist, and grows a bright white stripe across the indentation to visually break its body into what looks like 3 distinct segments. They supplement this shape with a specific behavior known as the antennal illusion. The spider lifts its front 2 legs and waves them in the air. By walking on the remaining 6, it creates a nearly perfect silhouette of an ant feeling its way through the environment. Looking and acting dangerous works incredibly well against predators like birds and wasps, but this is strictly an optical illusion, and it falls apart entirely in the dark. Some of the richest sources of food in the forest are located inside the ant nests themselves. To access this heavily guarded, pitch-black fortress, visual costumes are useless. Instead, a variety of parasites employ myrmecophily, a strategy of bypassing visual detection altogether to live safely and feed directly alongside their hosts. Inside a dark colony, ants rely almost entirely on smell to identify friend from foe. Certain species, like lichanid butterflies and parasitic wasps, bypass these sentries by secreting cuticular hydrocarbons that match the colony's specific brood pheromones. When a worker ant encounters this chemical lye, it doesn't recognize a threat. It reads the chemical signature of its own young, meaning the invader is actively fed and protected by the very soldiers meant to kill it. An even more precise close-quarters deception belongs to a microscopic mite known as planodiscus. It survives by physically clamping on to the leg of an aggressive army ant. To avoid being pulled off, the mite mimics the ant at a microscopic level. It develops the same cuticular sculpturing and replicates the bristle count found on the surface of its host's leg. When the ant pauses to groom itself, its tactile inspections fail completely. The physical sensation of running its legs over the parasite feels like grooming its own exoskeleton. By defeating the chemical and tactile senses of their hosts, these mimics bypass millions of years of fortress evolution. They gain free access to the colony's resources, converting the most dangerous insects in the forest into their personal bodyguards. So far, we've looked at mimicry as a static, lifelong costume, but biological deception can be dynamic, shifting to meet the demands of different environments as an animal ages. Few organisms demonstrate this better than the phasmid Extatosoma tiaratum. To survive to adulthood, it executes a sequence of 3 distinct survival strategies. This diagram illustrates the first stage. The mother drops an egg featuring a specialized fatty nub known as a capitulum. This mimics the oil-rich seeds that ants collect for food. Tricked by the reward, ants carry the egg deep into their protected underground nest, Stage 2 begins when the nymph hatches inside the colony. Surrounded by hostile soldiers, the insect immediately curves its abdomen upward and adopts a stark red and black coloration. It is performing a Bayesian mimicry of the toxic Leptomyrmex ant. Because it looks and moves identically to the dangerous locals, the defenseless nymph marches right out of the colony and makes its way safely up into the canopy. Finally, once it reaches the safety of the foliage, it sheds this ant disguise. The adult morphs entirely, expanding into a wide green leaf covered in physical thorns to deter passing birds. It survives its most vulnerable years by chaining these strategies together, starting with a physical seed mimicry, transitioning into a behavioral ant impersonation, and finishing with visual camouflage. In a forest packed with predators, survival doesn't always go to the fastest runner or the heaviest armor. Often the animals that endure are simply the ones best equipped to lie.